Now, in the previous section, we walked through a world without async await. Now, the good news is you'll likely never end up writing code that looks like this because, well, the async await operators do exist, and they have existed since C# 5. In fact, Microsoft with C# invented the concept of async await. The implementation was so well done that it now appears in nearly every single programming language almost identically. So let's jump back into this code and see how we can rewrite it using async await. Now, the first thing I'm going to do is remove console.readline because now our code will not be jumping around all over the place. We'll be able to read it top to bottom, left to right, without having to worry about the program, the console program, completing before our code in the background finishes running. So let's go ahead and get rid of this. And what we're going to do is replace this continue with the await keyword. And now we can remove that continue with and do the same thing here for the gravy. Now, one thing I do want to add is ready to eat here at the bottom. This way we know that we've reached the end of our program. We're done cooking the turkey, we're done cooking the gravy, and that now the food is ready to eat. So let's run this code and see what happens. Okay, the build succeeded. We see we're cooking the turkey. We're waiting for the turkey to finish before we start cooking the gravy. The gravy completes, and then we reach the line ready to eat. And what we're doing here is essentially using the same idea that we learned with that continue with callback method. But instead of us having to write our code in such a way that it jumps around and is difficult to read, with the async await keyword, we literally tell the program to await this line of code. So the same thing is happening where the program starts running, the main thread calls console.writeLine cooking started, it initializes the turkey, and then it hits this await keyword, and in the background, turkey.cook is running. And meanwhile, the main thread is waiting for this to complete. When turkey.cook completes, it calls back to the main thread, the calling thread, and then the calling thread picks up where it left off. So that calling thread, the main thread, comes back into here, initializes a new object, gravy. We call gravy.cook, but again, that main thread hits the await keyword, telling it pause its execution. Meanwhile, gravy.cook is running on a background thread. And while that's happening, if there were other things going on in our program, that main thread, that calling thread that started our program that called await gravy.cook is also able to do other things. It's freed up as well, and it's not locked into waiting until gravy finishes cooking to do other things that it may need to do. Don't worry if that sounds a little confusing. We'll cover all of that later on in this course. But for now, know that the calling thread is awaiting gravy.cook, and when gravy.cook finishes, it returns back to that calling thread to finish executing this program where it prints ready to eat to the console. And that's exactly what we see in our output. So here again is the code similar to the code we just wrote in our program. Again, the code's all available to you if you'd like to grab the completed solution. You have that in your materials, so please do grab it, or you're welcome to always follow along with me while I code. And just like we learned, when this code runs, and when we called specifically .NET run, we see that cooking started, that we cook the turkey first. We wait till the turkey's finished cooking because it's awaited before we start making the gravy. And then we await the gravy cooking until that's completed before we say that the gravy's completed and ready to eat. This reads much nicer. It's much more intuitive as a developer because step 1 is the cooking started. Step 2 is that we're cooking the turkey. We initialize the turkey in step 3. Step 4 of our program, the turkey cooks. Step 5, turkey completes. Step 6, console.writeLine making gravy. Step 7 initializes the gravy object. Step 8 calls gravy.cook. And then step 9 prints to the console that the gravy is completed. Step 10 is that it's ready to eat. And we see now that our code is much, much more readable because, again, we can read it top to bottom, left to right, and we don't have to worry about memory mapping the code in our head like we did with callbacks to know that the code execution is actually going to be jumping around. With the async await keywords, we're now able to write our code the same way we would read it, making our lives easier as developers, making sure that we don't accidentally introduce any bugs because of the way the code is jumping around. With async await, everything happens top to bottom, left to right. Now, everything we've covered so far is specifically asynchronous programming, where we're running code on a background thread with await turkey.cook and await gravy.cook without locking the calling thread. In the next section, we'll introduce parallel programming, and we'll look at how that's just a little bit different from asynchronous programming. See you then. Welcome back. Looking at the code from the previous section, we see what we're doing is initializing a turkey, we're cooking it, we're waiting for that turkey to finish, and then we initialize an object called gravy, and we wait for that gravy to finish cooking, and then we say we're ready to eat. But in the real world, if I were to say cook a Thanksgiving dinner, I could actually cook the gravy while the turkey's cooking. There's no reason for me to stop cooking and take a break while the turkey cooks, especially because, as you know, turkeys can take a long time to cook. So what we're going to do here is introduce the concept of parallel programming. And the way this works is that we can initialize our turkey and gravy objects here first, and then we can take advantage of something called task.whenAll. And what we'll do is inside of task.whenAll, this is where we'll call turkey.cook and gravy.cook. So instead of awaiting them separately, waiting for one to finish before the other finishes, task.whenAll allows us to pass in as many tasks as we want that are all going to execute in parallel together. So we're actually calling gravy.cook and turkey.cook at the same time, and this await task.whenAll will finish once all of the tasks have completed. So let's run this and see what happens. Okay, great. We see that we've started cooking. The turkey and gravy have started cooking immediately. And the gravy completed first, which makes sense because gravy takes less time to cook than the turkey. But we still waited for the turkey to complete. So we still waited for turkey.cook to finish before moving on to the final line to say ready to eat. So with task.whenAll, we can pass in multiple tasks that will all finish executing, and we won't move on to the next line of code until all of them are done, thanks to the await keyword. So again, here's the code that we just wrote, and we see that we start cooking both at the same time, but the gravy completes cooking before the turkey completes cooking. And then once they're both done, we can say that we're ready to eat. And similar to the last example with async await, we can read our code top to bottom, left to right. So step 1, we initialize the turkey object. We initialize the gravy object, step 2. And step 3 is when we await task.whenAll. So really what's happening here is there's a step 3a and 3b that are both running on background threads under the hood, and we're waiting for both of these to finish before moving on to step 4, where we say that we're ready to eat. And this is parallel programming, where we have multiple things going on in the background at the same time. The big difference here with parallel programming is we want to be careful to avoid what are called deadlocks. Say turkey.cook is dependent on gravy.cook to finish, and vice versa, gravy.cook is dependent on turkey.cook to finish. And now these both are waiting for the other to finish, so neither can finish. And now our code is just deadlocked because it can't continue. We're stuck here on step 3 until turkey.cook and gravy.cook are both finished. But if they're both waiting for each other because of a deadlock, then we run into another bug in our code. So do be careful. But in our async await best practices examples, we'll show you how to avoid any complications, any risks with our asynchronous programming and our parallel programming. Now, you've probably heard me use the words task and thread a lot, but we haven't defined them yet. So join me in the next section where we'll define what is a thread and we'll define what is a task. So far, I've been using a couple words, task and thread, but we haven't really defined them. So what is a task? Well, it can be found in the namespace system.threading.tasks, and essentially a task just represents an asynchronous operation. A task doesn't necessarily mean that it's going to spin up a new thread. A task doesn't necessarily mean that everything inside of it is going to happen on the same thread, and it doesn't necessarily mean that everything inside of it is going to happen on a calling thread. What a task is essentially an abstraction over system.threading.thread, and it allows us to not really have to worry about threads, thread pool management, switching tasks back and forth between threads, because .NET handles that for us under the hood as long as we use task. Now, a thread is an individual unit of execution. I like to think of threads as little mini programs because, as we know, when we write our code and we run it, all of that code gets loaded into memory, and step by step, the CPU executes each line of code for us. A thread is very similar to that, but instead of our whole program, it only contains the steps that it needs to execute to complete the thread. So think of a thread as an individual unit of execution. It's like a little mini program that contains all the steps it needs to run. Now, the cool thing with the thread is it also contains tons and tons of information under the hood about its own thread ID, this thread state, as you know, is this thread running? Is it completed? Is the thread still alive? What's its current priority? The current culture, like what language, what dialect the user has selected for their computer. So current culture is what can automatically switch languages and auto-detect what languages to show on the screen. Is the thread a background thread? And the execution context, which we'll dive into this deeper later, but it contains everything that this thread needs to know about our program. So things like what permissions do we have when we run this code? What level of access? Who called us? How do we return to that calling thread? All of that information is stored in the execution context. And essentially, the execution context helps .NET move between threads and allows threads to communicate back and forth with each other via the runtime. But don't worry too much about execution context because we'll dive deeper to that in our deep dive section on the .NET internals. So now that we've talked about asynchronous programming, parallel programming, what is a task, what is a thread, it's time for us to actually dive into the .NET code, where we'll look at what code .NET generates for us that enables all of the mechanics of async await under the hood in the .NET runtime. See you then.